Hi, everybody. Welcome back to another seminar with VTSS. And let me welcome Paolo Zaffaroni from Imperial. Thanks for joining us for your seminar today. And let me also, I think, welcome Riccardo Passeggeri, who might be in the audience, otherwise he'll be joining soon for the informal discussion of Paolo's work. The rules of the game are the usual ones, meaning if you have a question, if it's just a clarification question, just ask it during the talk. Otherwise, if you could wait for the Q&A, that would be better. Just unmute yourself and then go. You don't need to ask on the chat. We have an additional constraint relative to usual today, so we need to make it within 1 hour because both the speaker and the discussant will need to leave us in an hour. So we're going to keep the presentation slightly shorter. Just keep it in mind. Paolo, if you want to start, it's all yours.
That's well. Thank you so much for having me here. It's my first time in this series. Anyway, maybe some of you know me, and anyway, Paolo Zaffaroni from Imperial College, and also Sapienza Rome. And today we talk about a paper co-authored with myself, which is on factor models, which is my main research agenda. I mean, it's a method. So the paper is a methodology for empirical asset pricing. So usually my customers, if you want, are asset pricers. So I'm glad that actually I could maybe go a bit more into the technical details given the type of audience that we have today. Okay, so what am I about? It's well known that linear factor models are becoming very popular in asset pricing. Or actually have been very popular for a long time, in particular using a bunch of observed risk factors, which are typically returns on traded portfolios. But the problem, of course, is that over the decades, more and more factors were proposed, so that now we have so many that we talk about the factor zoo. The most prominent factors, I guess, that we all know are the Fama French factors, but as I said, there are hundreds and hundreds of those. Now, of course, this is cool, but they seem to perform relatively well. But of course, there's always a risk that either we are not including the whole set of risk factors, or that maybe we include something that should not be included, right? Some spurious factors, which also can be quite disastrous. And so more recently, I think empirical asset pricing discovered this, this idea of using latent factor models, in particular estimated PCA, which of course, has been most popular already in other fields of economics, in particular macro, and so that anyway, and the reason why these are sorry, somebody doesn't see the slides. Sorry, Michele, can you see the slides?
I can actually see them well. Can the others let us know if you can see them or not?
Okay.
I can see them.
Yes.
Okay, I'll carry on.
Marina.
Oh, good.
So yeah. Okay, so maybe the person says. Okay. Oh, it was Riccardo actually. Okay. Okay. So anyway, so latent factor models now, in asset pricing become more and more popular because, of course, by construction, if you estimate the space of risk factors by PCA, you are not omitting it. You're not doing anything else. Conditional using the right methodology. So that's one challenge that how it's resolved. The second, another issue is in asset pricing, roughly speaking, you can set the models in categories: unconditional and conditional asset pricing, which basically means that in conditional asset models, risk premia, risk exposures, and parameters in general are time varying. In fact, if you want conditional moments, and instead in unconditional asset pricing, the parameters are constant. Now, asset pricing theory, it is intrinsically dynamic because, in fact, prices are theoretically can be expressed as conditional expectation of payoff multiplied by the SDF. But of course, if you want to capture conditioning, you have to really sort of specify ultimately the conditional distribution asset returns. And we know that that's very, very hard in general, and in particular for asset returns. And so what people did was to sort of simplify, or if you want, parameterize. The problem is that once you parameterize, as Hans and Sargent, sort of famous quote, with tractability comes misspecification. And so here is like another possible flow of the methodology. So of course, in Imperial surprising, what was the reaction to this? If you want, pioneered by the famous, Fanon-Akbeth two-pass estimator is, well, why don't we just use short, time rolling windows, of data to estimate the model across time? Which, of course, as an econometrician, you can always interpret this as a non-parametric, Nadaraya-Watson estimator with a rectangular window, but the intuition is correct. And in fact, in a certain sense, empirically, people use it all the times, and it seems to do a satisfactory job. So what do I do in this paper? What do this paper? I essentially take those two problems aboard, and I join them in a certain sense. So basically, I'm not going to study. I mean, as the estimation, and in particular the testing, if you want, the performance of factor models for asset pricing when the factors are latent, and I'm using rolling window estimators. The engine is PCA, but because I'm taking a short time window of data, I call this local PCA, which basically means I need to study the behavior of PCA when you are dealing with panel where the number of assets, so the cross section size is very large, and the number of time periods is fixed and very small. Now, what are the beauty of this? In this way, we resolve the omitted risk factor issue and the misspecification dynamics issue. And to do this, and also by doing this, we are basically allowed to virtually have, bracket more or less net sum assumptions, almost every feature of the model to be time varying. So the load is to be time varying, the risk premium will be time varying, and so forth. Okay. So of course, challenges. The practice is beautiful, but as academics, we need to know a little bit about what happens really when you do that. And so the goal of the paper really is to provide some theoretical underpinning to this sort of traditional using rolling window, and in particular, what happens when you use it in a PCA context. Now, the theory of PCA, I will briefly go through it, is well known. Especially, we know that all the nice properties happens when you have this large data set, when both N and T are diverging, N be the cross-section size, and T be the sample size. But of course, when T is fixed, necessarily, you create some biases, right? So some stuff doesn't dissolve, right? And so the question is, how can you make this work? So how can you use a model? How can you test the appraisability of the model when T is fixed? And this is the technical challenge, and I'll tell you how I overcome this challenge. If you're familiar with the forecasting literature, there is this really beautiful paper of White, Geromini, Raphael, and Hal White, in which actually is very, very different. But actually, there is some sort of main idea I recently discovered, to be on an ex post, once I've written my paper. And what they do, they basically show how to test for pricing, sort of forecasting ability of using some econometric models. When the model has some estimates, some parameter estimated, which are, again, also sort of biased because the sample stay fixed. And in a way, the spirit is very similar. So in my case, again, I fix T, but I'm leveraging on N to get the asymptotics. Okay, so this is where the other dimension really, really helps. Now, one thing maybe, I guess, is a bit unique about this paper is that it's not another econometric paper, which I've written, many of them were about, we derived the distribution, standard errors, which is great, but I try actually to go a little bit beyond that and to really do inference on the pricing ability of the model and to pin down, tease out the properties of the object of interest that people care for in Imperial pricing, in particular risk premium, SDF, and mean variance portfolios. So to do that, what I'm going to do, the first job was actually to revisit theory. And in a certain sense, I wish I didn't have to do that because it would make my life easier. But when I sort of dug into the statistical literature or the economic literature, there were some gaps, right? In the sense that we didn't know, at least to my knowledge, and so far, what are the statistical properties of PCA. Or we know something, but not everything when N is larger, T is fixed. So this was the first thing that I did. And so let me also give you the insights of how this works, and then you see more details. Essentially, again, when the classical PCA requires both entity to diverge, but and then you estimate the factor, the loadings, etc., etc. However, it turns out that if you look more carefully at the mechanics, you realize that, in particular, the factors demand a large N, and the loadings demands a large T. Okay, so this is this sort of split, right, in the structure, and so this means that if I fix T, I can estimate the risk factor really, really well, but I'm going to estimate the loadings really, really bad. In the sense, if T is 12, they're super noisy. So then this seems like an impossible job. So what else? But then they realize, in a way, this is like one of the beauty, I think, of this empirical surprising setting is that a lot of objects of interest in a surprise, it turns out that are function of averages in the number of assets. The best example is the following. So think about portfolios, okay, mean balance portfolios, for example, right? So the portfolio in the invariant formulas are essentially almost linear in the loadings, right? So this means that every portfolio weight remains very, very, very biased, okay? So it remains random and biased. However, when you multiply these portfolio returns with the returns themselves and you construct the portfolio return, and then you take a sort of large average of these returns, suddenly the bias gets mitigated, or if not mitigated, there is a bias that arises that I can estimate. And so I do a nice bias adjustment. And so basically I can recover the correct portfolio return, even though my portfolio weights are biased. And the same stuff applies to SDF, and the same idea applies to risk premium. So in 2 words, this is really the key insight, if you want, of how the methodology could be used in this setting. So okay, right. And so basically, how do you use this methodology? I mean, there's a very long. I mean, the paper is not too long, to be honest. It has been cut for editorial, but it's a long appendix and lots of applications. How do you use it? I mean, I can see 2 different ways. One could be, one remains kind of semi-non-parametric. You don't specify any, dynamics, and you roll your windows, and they use the SDF and use the portfolio weights, etc. Or you can use my estimates as a sort of preliminary estimates based on which then you can sort of this will help you to choose which are the state variables that maybe are driving the dynamics, and then you can re-estimate a more structural parametric model using this insight. So both I think both ways are legit. I mean, I kind of like more the first one because I'm always very sort of careful and minding about misspecification, but in practice you can do either ways. Now large N, I mean, as you will see, this is part of my probably large, I mean, now my main research agenda, which is about developing methodologies for empirical surprising when the panel has an N large, it is fixed. And there are many reasons why I think this is super cool. One is sort of empirically justified because we have a more and more really rich data set of single stocks. In my application, for example, I have a panel of 20,000 stocks. And so I can be very rich in the cross section. At the same time, practitioners tell us that they're really concerned about structural breaks, non-stationarity. I mean, think about how many times the world has been changed in the last few years. I mean, is to think that the same model will sort of adequate in the last 20 years is of course heroic. And so tentative fix allow to mitigate this concern. And also theoretically, again, if you fish into a separate theory, you realize even the simplest model like the CAPM requires notion of large N, in the results. So the predictions are really require a large cross section. And so this, if you want to present a nice theoretical underpinning. Now, to do this job, I mean, the paper is quite ambitious in the sense that is really touching and advanced, if you want, 3 literature. The main one that I really refer to is the sort of, I call it PCA in asset price literature. And these are the main paper. I mean, there are many, but the paper that really sort of leverage, in particular, the Gilio Shu JP paper, Marcus Pelger, Marcus Pelger paper, and then I think also Gagliardini has some nice. Sorry, guys, I click and I went to I went forward. Okay, and then we have some nice paper, and then also some nice, important empirical paper where basically, Coates and Nacho Santos and the Tao again, and others where they demonstrate why estimated an SDF with PCA is, provides what's called a robust pricing performance. Then we have the conditional supply signature, right? And now here again, there are two avenues if you want to simplify. One is where you presume some state variable that you observe, and you simply assume that your parameters are, if you want, some linear function or some parametric function of these state variables. And then you carry on, okay? The best example, perhaps one of these examples, is a model that is going, very popular these days, which is the IPCA of Kelly and co-authors, but there are many others. Or otherwise, you just go non-parametric, meaning like you take this, kernel-rolling window estimator, which is the avenue that I am advocating, okay? Because of course it's sort of misspecification free. The last setting, of course, is the backbone at the end. There is this large N asymptotics in the PCA setting. I guess we all know this magnificent, important work on PCA in the double asymptotics. But as I said, for large N fixed T, there is very little. The most important work that I really use is the famous Conner-Coraci paper. They show that the consistency, if you want, let's say meta conjecture because of PCA for fixed N, and by show the necessity condition again for consistency. I sort of advance them, showing how you can do inference rates, etc., which is important if you want to do develop my testing or pricing ability. Okay, so as I said, I'm merging this literature and hopefully I'm advancing. Now, this paper is, it's not just one-off in a sense. It's part of this now large research agenda. I'm basically working mostly in this setting. This is what in finance we call cross-sectional surprising. And so I have several papers that are sort of touching different aspects of this. And the common denominator is that large N fixed T, and then there is a PCA element of it. Okay, maybe I can tell you a bit more about this. Okay, let me jump on the model. I have 25 minutes. Okay, so this is the statistical model. Okay, so XIT are, for now, let's say excess returns on some stock I at time T, and it's a conditional model. So all the parameters are conditionally time varying. So there is an intercept, and there are some latent factor, little f, and then there are some risk exposure lambda, and then there is an asset-specific component. Okay, so this is just a standard statistical model, except for the time variation. Now, one important insight is the following. So, and again, I think I really borrowing from asset priority theory to help me to solve some difficult statistical problem. And said it very simply, one of the problems of and large and T-fix is that PCA requires the idiosyncratic term to be quite nice, if you want. In particular, even though it can be cross-correlated, when you average of this cross-ratio, they should vanish, and so you basically get a spherical covariance matrix. Okay, so I need to get that. Now, this is okay, but the problem is that usually, when we got the data and we apply CA, the first thing that everybody does, for example, in macro, is to demean the data, right? So you just get rid of the intercept. But if you demean the data and T is fixed, even if you start from IID data, you immediately induce correlation, right? And that will kill my estimator. So I cannot do that. So the question is, so how can I crack my problem with the intercept? And this is really how I got my escape route. And no arbitrage, which I think is legit given the type of problem I'm looking. By no arbitrage, it turns out that the model has some features. In particular, you can rewrite the model in this way, where there is a sort of adjusted intercept, which I call a little a, which in finance we call it the pricing error, which is not completely unconstrained. In particular, it has to be square summable. And square summability at a very, so basically if you divide by n equals like 1 over n, why this is important is because then when you estimate the lambda, the f, if you do an OLS regression, you don't need to demean the data because the means will disappear. The intercept will disappear. Okay, so that is the crucial one, a very, very big help they got from the theory. By the way, this model here, so the factor model with no arbitrage in asset pricing is known as the APT model. So here I'm just taking a conditional version. Okay, so the other thing that is happening is that once you put no arbitrage, the factor get transformed. I mean, using the language of mathematician, think about it as like a simple change of measure. So actually it's a recentering, so that the mean of the factor, which I know we call F, big F, is not just anything, but is a specific quantity which happens to be exactly the risk premium of the factor, okay, which are well defined, using a separate theory. The paper has all details. I'm just abstracting here, but I think we all know what risk premium is, and so FT are centered around the risk premium. Okay, so identification. So what is it about? Now, another challenge. So when T is fixed, there is also an identification problem, in a sense that, again, if you want to pin down, identify risk premia in particular, it turns out that you cannot really quantify risk premia, which are called gamma, but you can identify what Schenken in his famous nephew paper called the ex post risk premia, which is the risk premia plus the factor innovation. Now, I mean, what does it matter? Well, it matters in the sense, of course, it means that the ex post risk premia is a noisy version of risk premia, is unbiased, clearly, but of course, that has a bit of noise. And so, but the point I want to make is that, remember, T is fixed. So in a certain sense, when you're working, when you live in a T fixed environment, in a certain sense, the parameters that of interest becomes immediately like sample averages. Sample averages, for example, this is the sample average of the unknown latent F risk factor for a given sample of size, capital T. So that is what I want to get, and that is what I can estimate consistently, okay? So anyway, so ex post risk premia. In the same way, in asset pricing, really, or in general, or in the finance, what you really are after, essentially is the SDF, right? The SDF is the, well, is this, semi-martingale, if you want, quantity that is represent the synthesis of the asset pricing model. Once you got the SDF, you can price any asset by multiplying the SDF by the payoff, and you take the conditional mean. And that's why I said the prices are condition expectation, because of this. Okay, so this is really sort of ABC of asset pricing. So we want to get to the SDF. The SDF in a factor world is spanned by the factors. So the point is, okay, so how do we estimate this guy? But first of all, remember that because we are in the ex post fixed environment, this is really the SDF you can estimate. I call it big M, if you want the ex post SDF, which is a function of the sample, so mean and the sample covariance of the F. Remember, everything is latent here, so these are all parameters in a sense, right? Anyway, so this is the object that we want to estimate. Now, you might be curious to say, okay, because you can never get this, you cannot identify this, but you can identify that. And that is a function of averages. How useful it is for pricing? Well, now here mathematics is helping us a little bit, because it turns out that given that the SDF is used as an argument of an average, of a time average, then the time average is essentially smoothing out, right? And is pushing up the rate of convergence. So now we basically have that this quantity, when the model is correct, will go to zero very, very fast. If you let T grow. So in another sense, rather than having the usual square root T rule, which is the one you get when you do estimation, the pricing performance is much, much stronger. Okay, so anyway, these are the population parameters. Okay, so let's go into estimation. First, I'm going to tell you about the sort of 2 words about the local PCA, and then how is deployed to get the parameter. Okay, so this is just the standard PCA. It's nothing biggie. The only thing I want to emphasize is these are PCA evaluated for a given time interval, which of course I imagine is an application that is now I'm going to roll this, right? So these time intervals of small size capital T are indexed by this little t, which is the time index that runs through time. Okay. Anyway, you just PCA, eigenvalues, eigenvectors. So the factors will be the R-1 eigenvectors normalized of the matrix X transpose. Notice I don't do any demeaning. And the lambdas will be simply the projection of the data on the factors. Okay. And you can have a kernel PCA interpretation, but I mean, as I said, because T is fixed, I prefer not to push this very much. Anyway, so once you got the estimates, then you can estimate the risk premia. So this is the gamma tilde is the estimate of the risk premia. And nice feature is that, again, for the ones of you who kind of are familiar with empirical asset pricing, how empirical asset pricing estimates risk premia using the famous 2-pass estimator, the FAMAC estimator, which is this quantity here. right? So it's a regression of the lambdas of the loadings on the average return. Beautiful result. Turns out these two guys are identical because of the orthogonality induced by the PCA, sort of, singular value decomposition. So anyway, so in other words, my estimator is the two-pass estimator. And then, of course, you can estimate also the SDF. I just do plug-in, so I plug in the values, and I get my estimate of the SDF. Now, one thing which I didn't mention, but probably obvious, is that remember in a latent word, everything is cool, but except that it is always an unresolvable identification problem, meaning that you can always estimate the fact in the loadings net over rotation, which is unknown. Does it matter? It turns out that, well, it depends. It depends what the use is. But for example, if you want to do a forecast exercise, let's say, then it doesn't matter because what matters is that you just need to, include all the factors which are spanning the right space, so that the R square of predicted R square will be identical. In asset pricing, likewise, for example, this quantity here is easy to see that is rotation invariant because the rotation matrix will pop out, because of the maths. And the same for the mean variance portfolios. And so that's actually, I think, quite a nice feature. So we don't need to worry about the rotation. Although there is a caveat I'm going to tell you a little bit. Here, I'm just tell you that, we talk about dyspremia, we talk about SDF, and finally, another, classic application is the mean variance portfolios. And here I'm just laying out the main notions of the portfolio that we can estimate with this technology. Okay, so these are how you get the estimates, how they behave. Okay, so here I have summarized the asymptotic properties. Basically, two results. Here I have the root n convergence of the factors net of rotation. H is this unknown rotation matrix, and then I have a CLT as well. One thing which is interesting is the fact, of course, because this is local. What happens is that basically I'm going to have a rotation matrix that can change potentially across time. So I have a sequence of rotation matrices, which could be tricky. I'll tell you how I handle this. Now the last result is a reminder that like when n is large, the factor, remember what I told you, right, consistent, but the loadings are not, and that's exactly what happens. Okay, so basically here. This shows, towards why, what is the type of bias. So there's a random quantity that is affecting the loadings, which of course you can see will go to zero only when t is large. Now, so what? So, well, the good thing about this result is that even though the lambdas are biased and random forever, if you want, you can consider estimate the moments. For example, you can see if you take the sample mean of this guy here, is going to be equal to this quantity plus the sample mean of this guy here, which of course is going to go to zero because this is a zero mean quantity. And so sample mean will be consistent. So and then if you take the variance, for example, if you square this, then you get the square of this, and then you get the square of this. And so again, now in this case, this guy will not go to zero, but it can be estimated. So I can have a consistent estimation of the bias. And so this means that I have a very natural bias adjustment estimator. And so I can recover even the second moments. Now, this is important because I need these quantities when I calculate the standard errors on my quantities. Okay, so and so I need to estimate this quantity clear. Okay, so in latent factor model, there is also, of course, before you do all this, you need to decide, to speak, how many factors you're going to choose. Now, again, the existing technology. So I also do some other work, on frequency domain, on estimating number of factors. Really requires large NNT, so I had to scratch my head a little bit. But it turns out that actually, if you can actually construct a penalization quantity so that I can go at a criteria that gives me a consistent estimator of the number of factors, which, by the way, can change from window to window. Okay, so that's again because of, remember, my aim of having a conditional asset pricing model. Anyway, so okay, so rotation. I think I'll tell you. Already told you about this. The only thing to say is that because we have this issue of the rotation matrices that change over time, then if you're aiming to find the long time series of your estimated factor, then that wouldn't work, right? Because you're mixing apple and pears. However, Pelger has in very nice paper has some conjecture about how can you basically map all these different metrics into a single matrix? So it's still a no, but it's only one. And in the paper, I show you how you can mathematically resolve this problem. And so basically, I can basically glue together these estimates and provide a long-term series if you want to. However, one of actually writers told me that another maybe good aspect of this of my framework is that you can actually go in the other direction. Say, oh, what about if there are some factors that are only living for a given amount of time and then they dissipates? I call it locally strong factor. Best example could be the COVID factor, for example, or some event that is affecting the world and then somehow gets resolved. Or it could be a monetary policy shock. Anything that is unexpected and then it dissipates. Well, by definition, if you want, by construction, I can capture exactly these guys. Right? I can tell you exactly what happens in that particular window of time. Anyway, a bit more asymptotic, so you can, let's see how much time I got. I think got 10 minutes. So, you can have the asymptotics for this premia, and then you can estimate the standard errors, and then estimate the asymptotic for the SDF, standard errors. That's all cool. But I think what I really like a lot is this part here. So in a way, remember, our aim is to have a model and to see how does it work economically, right? So what are the economic gains they use with this model? So not just to say, oh, the standard error, the T ratio is 1.97, which is also cool and important. I mean, of course. And so here, let me tell you what I do. So here, on this page, I define how in finance we define performance of models. And there are many, it depends on the metric you choose. But there are probably two categories of pricing error. I call it pricing error from expected return, which is basically the difference between the expected return of the data and the model implied expected return. And then we have pricing error from pricing. So basically, I price, I take the SDF, I get the price of these payoffs, and then I check whether these quantities are zero or not. Okay, so this, and so if the model is correct, remember we're in the APT framework, so there is always this sort of little mispricing given there, but it's very, very small and it's dissipating. And so instead, if the model is missified, these deltas and this H will become very, very large. Okay. So I would like to test for this. I want to test whether the deltas and the H are small or not. And that's how I do it. Now, of course, big challenge, of course, is that with a second, but T is fixed. And so when I do my asymptotics and I construct my empirical pricing error, so here's just an example of the delta pricing error, of course, the delta pricing error contains, a big part of them will be simply the estimation noise that is induced by the large T, right? Which has nothing to do with the performance of the model. And so then how do I do this? And here's the idea. Well, I just take my deltas, I square them, and then again, I average them with respect to the number of assets. And by doing this, essentially, I'm like taking the average square of this quantity. This creates a bias, but is a bias that I can estimate, and then I subtract. And then basically, in a certain sense, I'm able to separate the pricing performance of the model from the statistical noise induced by fixed T. And that's what I do, okay? So here I have some result that shows you the sort of pricing test statistics that you can get, right? And in blue, I reported the bias adjustment, which are not, it could be very sizable, but they're nothing to do with pricing performance. It's simply because I'm constraining myself to have a fixed T because I want to capture conditioning. So I have a few more minutes. Okay, and then also another part. This is about like pricing performance in terms of portfolios. I can construct Sharpe ratio, wider risk, expected drawfall, and then I can construct, for example, confidence bands for all these quantities if I want to be serious and I want to quantify how my portfolio is behaving. Okay. Okay, lots of extension. For many different reasons. For example, today I was talking with my colleague. We discussed about making an application apply to exchange rates, and he says, okay, but we don't use the risk-free rate to excess return. So we need to allow for what is called in the theory like a zero beta rate. So we have an extra parameter. Now this wouldn't be too bad in a normal setting, but remember, I cannot demean here. So this gamma zero, it doesn't dissipate, right? So this guy, the A will dissipate by no arbitrage. This guy will not dissipate. So how can I get rid of this guy without demeaning? And so basically I show you how you do it. And the idea actually is I can demean not in time, but in the cross section. And somehow, with some miracles, I'm able to resurrect all the properties I want to for the cross section demean quantities. And then, in fact, I can even provide an estimate of the risk-free rate, of the zero beta rate. Okay, so that's done. And then, okay, mean portfolio. I mean, here really I'm referring to, the classics of the APT. I don't know if you're familiar with the Chamberlain-Rothschild papers. And basically, there is this idea that, PCA are effectively portfolios. In fact, PCA are linear combination of the data returns, so they are indeed portfolios. But actually, it turns out they are, in fact, asymptotically equivalent to what in finance are called the mimicking portfolio. So portfolio that are constructed to mimic a non-tradable risk factor. Okay, so this gives you a bit of underpinning. I mean, it's not important for the empirics, but underpinning. Okay, so empirics is voluminous. I only give you probably a peek to this. I'm using an unbalanced panel of single stocks downloaded from CRESP, about 20,000 stocks. And I have about 480 observation in total, which I'm not using together. I'm using with small rolling windows of 24 months. So basically 2 years of windows. And I also have I also check what happens when you have a slightly longer window of 10 years, which is not unusual in empirical work. Now, this of course is a balanced panel. I mean, and I was asked to try some result with the with a classical PCA analysis, and the classical PCA is the one that takes all 480 observations. And of course, the point is that if you take 480 observations, the panel reduces dramatically, right? Because some stocks don't exist always across all these years. And in fact, the panel now becomes much smaller. And so I could also produce results for this balanced panel. So you would see 2 sets of results. And I do this just for the sake of comparison, to have a clean slate here. Okay, so what I got in the paper, I have several exercises. So I have some Monte Carlo exercises where I see how the methodology works, how my number of factors, time variable factor works, and so forth. And also, I think, again, it's interesting how this works with other sort of competitors that exist out there. In particular, I was asked to look at the IPCA and to see how it works. But perhaps more interesting is to look at the empirical parts. And this is basically divided in 3 parts. So I first look at, whether there is evidence of time variation in the data, and the answer is yes. And then I look at some statistical performance, R squared and parental composition, and then finally look at the pricing performance, both in terms of risk premia, SDF, and portfolios. I don't have time to do anything with this, so I'm almost done. So let me just show you 2 pictures. So one is, this is my estimate of using rolling window 24 observation of the number of risk factors. And you can see that, and by the way, the green line is what you get when you estimate the whole data altogether. So 1 risk factor, which is the kind of classical result. But what I think interesting is that not only there is a lot of time variation, but it's a time variation that makes sense. If you notice, the gray area are sort of financial crisis and market crashes. You can see when there is a market crash, 2000, 2007, boom, the number of factors just go down, which is what we expect because, common sense from financial markets that when things go badly, as there is the cross correlation spikes up, which means that in effect you're thinking about a model with 1 risk factor. And when things are going well, instead you can see that different asset market they span different risk factors. So things the number of risk factors globally will kind of increase. And I think this is an sort of unconstrained estimates. I'm not imposing anything, but it seems that it's finding this stuff here. Okay, I thought to show you 1 picture. So let me show you what I'm about to show you here. Let's see. A lot of stuff. So it's the performance. Let me see, price performance. Maybe pricing performance. Yeah. Well, I should tell you what. So let me go to 2 cool applications. So one application is about, for example, the extent to which I can sort of span the market return. This is a question that is bothering, us financial economists forever. It turns out that it does a pretty good job. If I look at the dominant PCA, the PCA1, if you want, and locally estimated. Then actually, oh, here it is. So in this picture, for example, in these two plots, I plot the histogram of my estimates, which is this, on the left-hand side is the gray one. So it's always the gray one, sorry. And on the left-hand side, you can see that the red one is the market return, okay, which is super noisy. You can see that, I mean, they're correlated, to be honest, positively correlated, but, it goes all over the place. And then on the right-hand side, I was asked to compare with the rather popular measure of expected return that is divided by Ian Martin using options. So he has a lower bound, or not bound, remember, on the market return. And they seems to go together, even though I'm not using option data at all. So I thought that this local approach seems to capture pretty well this quantity. And the second cool application, I think, is weak factor. So I will not say anything here. It's a huge field. I'm also doing some work here. But the point I want to make is that by construction, remember, my work is locally. So I can estimate stuff that exists only ephemeral for a given point in time, and then they disappear. And, in finance, there is a lot of work. And as I said, I also have a paper on this in progress, on, a lot of interest, because these are weak factors. Weak factors working towards factors that are sort of transparent to PCA. They pass through the net. So you cannot pin them down with PCA, but sometimes they carry a sizable risk premium. And so, for strategies and asset allocation, they can matter a lot. And so my methodology, I think you can sort of select them. And here I just have one application and one Monte Carlo. So just to give you an example, here, for example, I simulated an environment with two factors, one strong and one weak. One can disappear and appears, and you can see that with my local, which is second factor, with the local factor, I mean, it seems that it's working well. Whereas if you were to use the constant PCA classical approach, you will classify this as non-existent almost, right? Something that is not there. Instead, it's there when it matters. Okay, I just wrap up and just go to the last one. Here it is. Okay, so what I show you here is a new methodology to estimate conditional asset pricing model when they're driven by latent factors. Valid valid when n is large and t is fixed. I need some assumption. I haven't sort of told about that, but under some assumption, which are probably relatively mild, you can estimate feature where a lot of things are time bearing, like loadings and this premium in particular. And there is a lot of empirical application numerical work that sustain this work. And so that's all I got for you. Michele, shall I? I think Riccardo, shall I give you the